Thank you for the kind introduction. I'm from TRUMPF, and TRUMPF is also part of the Utah Consortium, where you will find the booth outside, and I'm also a member of TRUMPF, the quantum association of companies in the state of Baden-Württemberg. So when we look into industrial optimization problems, most of them are NP-hard. If they're not, they're probably solved efficiently already. But when you look at NP-hard problems, especially then inside the quantum community, it's often claimed, oh, it's NP-hard, it must be hard to solve. And that's not necessarily true. Some of the NP-hard problems are actually hard to solve in practice, but some of them are not. For example, the traveling salesman problem, for all means in industrial purposes and the metrics given, we usually have a very good heuristic. And then there's linear programming, for example, which in the worst case is NP-hard. But if you're thinking, wait a minute, I sort of solved this during my studies and that wasn't hard, right? Because the average case certainly isn't, and there's only a bunch of problems in that problem class that are actually hard to solve. There's a difference, though, as to why industrial optimization can be really hard. And I've brought the job shop scheduling problem for sheet metal manufacturing as an example that TRUMPF is very much involved in. And some of the complexity comes from scheduling problems being NP-hard in practice, because there are combinatorics in it. But then it gets worse because there are more constraints to it. It's not just about the jobs and the tasks being scheduled onto machines. It's also about worker skill, worker availability. It's about raw material availability. It's about the scrap rate that you get when you combine different orders onto a single sheet to be cut on a cutting machine. It's about the setup times, especially when you look into bending machines, for example, where you need different tools for different types of bendings. So the scheduling, the ordering of different tasks has a severe effect onto setup times when you look at it over a week or a month or so. And all of these different constraints need to be handled so that in the end you get a result that people on the shop floor can actually work with. And that is different to just handling the combinatorics inside your NP-hard problem. Okay, so how do we usually do that with classical solution approaches? And I think one of the most typical methods is you model it in some form of a standard problem, and then you use a standard solver to solve that model. For example, modeling as a MILP and then using Gurobi, Cplex, or R tools, any kind of optimization solver that is out there on the market. But that certainly isn't the best way of solving optimization problems in industry. And when you look in it deeply, you need customized heuristics in order to get the best results out of classical compute. And one of the, I think, more interesting questions always is to ask, if you do have an NP-hard problem inside of your larger industrial complex, is there a known polynomial time approximation scheme? And if yes, use it. And that's, for example, true for the traveling salesman problem. We know how to efficiently approximate it up to some bound. So you should always take that path, because it means you can quickly reach at least some value of optimization that you know is so you can get a certain quality metric, and you can get it quick. And if you don't have it, so there's no p-test, custom heuristics will still be much better than going with sort of standard modeling techniques and using standard solvers. But then again, that approach needs much more time, much more data, much more thinking about it. And so for the job shop scheduling problem at TRUMPF, we've gone that way. So we started off 4 years ago with sort of standard modeling techniques and rather standard solvers, and then step by step moved way more into advanced algorithmic ideas. The ones listed here seem trivial, divide and conquer greedy, but we started off with a p-test first, and then we had to bridge the last bit, and that was mostly done through parameterized complexity, so where you try to push the complexity of your NP-hard problem onto a different number. Usually, for example, when you think about job shop scheduling, it scales in the number of jobs that you have. And what you can do is sort of turn the whole problem around in a way that the complexity depends exponentially on the number of machines, which for a given job shop isn't as bad because the number of machines is fixed. So that's roughly the idea of parameterized complexity. And then we programmed that, of course, in C++ and use special compilers, and now we're down from days of calculation to less than a minute. Okay, so how do you do that in quantum? Well, usually, I guess for the last years, the approach in industry has been, let's model that as a QUBO, and then you can either go to quantum annealing straight away with companies like D-Wave and the like, or you can run it on any hardware that's gate-based with the QAOA algorithm. And there are, of course, further paradigms. I can't list them all. It would take way too much time to go into exact the actual algorithms based off these paradigms for all the different problem classes that we look at. Some of them are Grover search, so it's like searching unstructured database, which has quadratic speedup over brute force. There's quantum phase estimation, which is the backbone of Shor's algorithm. And there's Gibbs sampling, which is a Markov chain Monte Carlo algorithm that runs fast. It's basically sample out of a space of a multitude of different variables. Now that does come with certain limitations, though. Whichever quantum approach you're taking, you're just using a quantum physical device to calculate, and that comes with clear bounds. So most of you are hopefully familiar with these problem classes of classical theoretical computer science, where sort of the class P is problems you can solve in polynomial time, and we'd call that efficiently solvable. And then there's the bigger space of NP, which are kind of hard to solve, and the hardest of them is NP complete. And then there are even more classes out there. An interesting one for quantum is bounded error quantum polynomial. It means you can run it in polynomial time, so efficiently on a quantum computer, and it also has bounded error, which is more of a theoretical side remark, because quantum computers are stochastical machines. You've got to ask the machine a couple of times and then see what the distribution is like, and if you do weird stuff with error probabilities, otherwise you can sort of trick it. And this BQP runs diagonal to the otherwise well-structured classes shown. So it's the dashed line. Everything that's in P is also in BQP, and then some problems in NP are also in BQP, but the NP complete ones that we talked about before also are not in BQP. So there's no general exponential quantum speedup. All right, now that is bad for industrial optimization, of course, but it's also good for cryptography. And what for example, the paper shown below shows is that problems without a certain abelian group structure behind them don't have a greater speedup than n to the power of 4. So beating classical computers, even if you did go for the n to the power of 4, has other caveats. I think as a community, we've seen that scaling NISQI qubits will have a hard time beating classical compute. And I think we've also seen that today already, people are turning towards fault-tolerant qubits. The second thing is clock speed. So usually in computer science, people look at the number of steps you need to take in order to solve a problem. But how fast you are in seconds also depends on how many steps you can take per second. And currently, classical computers run in gigahertz, whereas most quantum platforms run kilohertz, if at all. And so quantum is up against orders of magnitude in lower clock speed. And that's a problem. Probably the only platform that is an exception is photonics. But the two things that hardware providers need to look into in order to create value in optimization is fault tolerance and high clock speeds. The graph shows how the steps you need to take scale on a quantum computer and a classical computer, and that there's a certain crossover point. And in the paper shown, they estimate for a single NVIDIA GPU versus a hypothetical quantum computer that hasn't been built yet, and probably no one knows how to build, that this crossover time and size means you calculate somewhere between a week and 2. And honestly, at TRUMPF, I don't think we have many optimization problems that we calculate as long. Classical compute, by the way, is moving. And a lot of what the quantum community says is, look, Moore's law is ending, we need to move into something else. And Moore's law is that the number of transistors on a given chip doubles roughly every 1.5 or 2 years. Mr. Moore was rather unsure about that and later on published something else, but roughly that's what's happening. And the effect is that the cost of compute is drastically decreasing. Now, why are people claiming Moore's law is ending? Because the structure size is roughly approaching a single nanometer. And once we reach somewhere there, we will get that a classical CPU will have quantum effects in it. And that is a big problem because you have built a quantum machine without wanting to do that, and you will not be able to get proper calculations out of it. That's roughly the claim. And together with ASML and SAIS, TRUMPF is pushing towards that. But a different view is that Moore's law isn't even that important for classical compute, because in classical compute, we usually use von Neumann architectures, which means we have a compute core and we have memory. And the data, as well as the instructions of that compute, is stored in the same memory, and we have a single line that communicates between the memory and the compute. And so one of the bottlenecks of this architecture is that you need a really beefy communication line between those. And if you have the best kind of compute, you're going to be limited by the communication. And so NVIDIA, for example, recognized that this was going to be a problem if they put together a lot of their GPUs in a single place, say 1,000. And that's why they started building this NVLink standard. And you can see here how the NVLink standard has grown in gigabytes per second. So we're currently sitting at 1,800 gigabytes per second. So that as long as you put together about 1,000 GPUs or so, they all act as if every RAM would be the single GPU's RAM. You can access every one of those thousands memories as if it was on the chip. That's roughly what those numbers mean. And if you ask me roughly how that looks, it's going to continue. And that is going to push classical compute on that side very much. All right, now that looks dire for quantum computing. What are the opportunities? Well, for one, don't focus so much on speedups. There might be different advantages. There might be increased energy efficiency, because if you run a data center with 1,000 NVIDIA GPUs in it, that's certainly a big power bill you're getting. It might also be higher modeling efficiency. So if, for example, we didn't have to go through 4 years of custom heuristics design in order to reach a certain thing, but if we could have reached, say, results we had last year with a lot less effort on a quantum machine without getting the speedups versus classical, we probably would have gone that way. And I think that's given how theoretical computer science looks at it, the potential for exact solutions is very much limited, because n to the power 4 is probably not enough, at least for the next decade or so. But in heuristics, the space seems very open. NISQ might not be the way, and for FTQC, we don't really have that many heuristical algorithms yet. And I think a big shout out that we need more algorithm development in that space. Of course, if you look in quantum computers generally, and that's also a bit of the slight shift we've taken at TRUMPF, there are more opportunities on the quantum physics material science side. But of course, those would not be considered as optimization. All right, so summing up, Some NP-hard problems are hard in practice, and some are not. The best classical algorithm is often not known, but running a model in Gurobi Cplex is certainly not it. The quantum speedup for exact solutions to general optimization problems is limited at n to the power 4. High clock speeds and fault tolerance will help quantum hardware to close the gap to classical hardware. And classical compute is a moving target. It will still make progress for the next decade at least in hardware and in software. On the opportunities, there's more than speedups to be looking at. Quantum heuristics is probably the way to go, but in order to make that successful, we need more algorithm development. Thank you so much.